Okay, this is Discrete Optimization Constraint Programming Part 2. Okay, so this is the goal of the lecture. Okay, so we're going to illustrate more complex constraint propagation. And the underlying topic is the fact that every one of the constraints in a constraint programming system has a dedicated algorithm. Okay, so that's the technical part. Okay, so what we're going to do from a non-technical standpoint is that for the first time you're going to see a complex propagation algorithm if you have never seen any. And it's kind of amazing how these things are working, the kind of information that you are deducing. It's like, the first time you see this is, wow, this program is actually pretty bright. Okay, of course it's not, but anyway, so it's going to give you a sense of what a constraint propagation algorithm is doing. It's kind of interesting. Okay, so remember, constraint programming is this combination of branch and prune. Pruning is removing value from the domain of the variables in a first approximation. Branching is, you are stuck, there is no propagation. You decide whether, you assign a value. You decide to split the problems into subproblems. Typically, you take a values and you start giving all kinds of values for it, in turn. Okay? And then obviously, once you branch, you apply the constraint propagation algorithm to prune the search space again. Now, pruning is basically, as I told you, using the constraints for, removing as many values from the domain of as many variables as possible. Okay? Branching is, in a first approximation, we'll see more sophisticated branching scheme later on, but essentially trying possible values for the variables. Okay? Remember, we had this beautiful separation between the search engine and then the constraint store. Okay? And so what is happening is this guy is basically trying to see if the constraint is satisfiable. And when it has derived as much information as it can, the search will make a choice and send a new constraint. And the constraint store has to be able to say yes or no. Okay? Am I still feasible? Okay? Or not? Am I infeasible? Am I infeasible? Okay? And if it's feasible, if it believes it's feasible, it's going to say yes. As far as I can tell, I'm feasible. And sometimes, you add a new constraints, and then the system will say, oh, no, I'm infeasible. Remove that choice, give me another choice. Okay? So that's basically the essence of constraint programming. The inside of this constraint store is very interesting, right? So you have the domain store here, which is basically capturing the search space, typically associated domains to every one of the variables, and then gravitating around it are all these constraints, okay? And they don't know about each other, that's the key point, okay? And these constraints have two goals in life. I told you they basically are asking themselves, ooh, am I feasible with respect to this set of domains? So can I find an assignment for the variables using these domains such that this constraint is satisfied? And then they will say, ooh, but can I actually knock down some values in these domains such that I reduce the search space? Okay? And of course, as soon as you do that, some of the constraints may become infeasible, or some of the constraints may be able to knock down more values from these domains. And that's the constraint propagation algorithm. Okay? Right? The constraint does two things: feasibility checking, is it still feasible in the set, we're given the set of domains, and then pruning, given the set of domains, can I knock down some value for the domains of the other variables? Okay? Now the key point, and this is one of the topics covered today, is that every one of the constraints in a constraint programming system has a dedicated algorithm to do these two tasks. Okay? It's going to test feasibility using the semantics, the structure of the constraints, and it's going to do pruning using the same information. Okay? So this is a strength of constraint programming. It can exploit the structure of these constraints to prune the search space as best as it can. Okay, so I'm going to use a very simple example: send more money. Okay, the story here is that this is a graduate student going to school. He needs more money, so his father is and his mothers are very reluctant to actually giving money, and so every time he asks for money, he has to find a clever way of asking. And so here he sent his parents a puzzle, and that puzzle is if the parents solve the puzzle, they will know how much money the graduate student wants. Okay, so that's the story. So essentially the puzzle has three words: send, more, money. Okay, right? And the amount of money has to be essentially the value of these letters over there, and you have to make sure, of course, that the addition here is valid. Okay, so in a sense you have to assign different digits to all these letters such that this addition is valid, and then you will have essentially the amount that needs to be sent. Okay, so now I'm going to show you one model, okay, for solving this puzzle using constraint programming. It's not a good model, okay, but it's it's just a model for illustrating constraint propagation. So a big disclaimer in many of the examples that I'm going to use the entire class is that there are many models that should be better than the ones that I'm proposing. They are typically chosen to illustrate different principles. Okay, so this is a model like we would do in kindergarten, in the sense that I'm going to do column-wise, digit-wise addition and use carries. Okay, so when you look at this thing here, okay, so you can see that I'm going to start with the value d and e and summing to y. Okay, I'm going to get a carry c1. Okay, and that carry is basically going to be used for the second column, and then I'm going to generate another carry for the subsequent one, and so on. Okay, so in a sense, the decision variables here are going to be of two types. They're going to be the letters, okay, or the initial letters of the puzzle, and then they're going to be the carries. Okay, and the letters can take the value between 0 and 9. They are digits. Okay, and the carries, of course, will take the value 0 and 1. Okay, so that's the basic principle here. Okay, and so this is one of the models. Okay. That you could write. I told you this is not the best model that you could write, but this is a model that will illustrate constraint propagation nicely. Okay, so what you see at the top over there, okay, so these are basically all the letters that you have. Okay, so so in this particular case, you have the letter S, the letter E, the letter N, and so on and so forth. You have then a range for the digit between 0 and 9. And then you have the two sets of decision variables. Okay, so you see the decision variable value for every one of these letters, okay, which have to be in digit, okay, between 0 and 9. Okay, so for every one of these letters that you see at the top, you will assign a particular digit. Okay, and then you have the carries. There are 4 of them, and the value between for the carries are 0 and 1. And then what you see here are all the constraints of the problems. Okay, so the first one are basically telling you that all the letters have to be given a different digit. Okay, so this is like in the map coloring or in the Queen's problem. Okay, basically not equal constraint between all the variables. Then you see that the value for S and for N have to be different from 0. These are the most significant digits of these two numbers, so you want them to be different from 0. Then you have the value that the carry for the last carry has to be equal to m when you actually look at this particular equation. Okay, so this is the last column. And then essentially you have all the other constraints that are looking at every one of the column and putting and expressing the addition. And it's always, in general, it's always one carry plus a couple of digits, okay, for the letters, and then on the other side you will have one other digit, and you will have essentially 10 times the carry. And that's what you see for every one of these constraints. So you always see the 10 times the carry at the end of the equation. Okay, so that's essentially the model here. Okay, so it's a set of not equal constraints, an equation, and then a set of other equations carrying, basically every one of the addition for every one of these columns. Okay. So this is the search space, okay? So the search space initially, what you see there are all the digit values, okay? And you see all the letters over here. You see also the carries there, and these carries can take only the value 0 and 1, okay? And once again, the key point here is that we are going to knock down many values from this search space, and that's the goal. And in this particular case, there are two things that are going to be interesting. Is how much we prune, okay, using these constraints, and it's also the constraint propagation itself. We're going to do something with one constraint that's going to wake up another one, which is going to propagate again, and so on and so forth. And that's this kind of propagation which is interesting. And this is what we are trying to illustrate today. Okay? So this is essentially the beginning of the propagation. Okay? So you have the not equal constraints. These not equal constraints are not doing anything initially because the variables have all the possible values. And then you have this interesting thing here that basically S and M cannot be 0. Okay? And then that m has to be equal to a carry. Okay, so there are a couple of interesting things that are going to happen there. Okay, so when you see that that s cannot be 0, you're going to knock down the value 0 from s. When m is not equal to 0, you knock down the value 0 from m. And then you have this interesting constraint, which is basically saying that the carry 4 is equal to the digit assigned to m. Okay, no, the carry is 0 and 1. Okay, at this point, essentially m is 1 to 9. So there is only one value which is common to these things, and that's the value, that's the value 1. So these two guys are going to be assigned to 1. okay? And that's what you see here. Immediately the system is deducing that, okay? And obviously once you do that, you know, m, you know, every digit, every letters, of course, has only one value, so there, you know, all the other values are ruled out. You also know that all the digits have to be different, okay? So basically these non-equal constraints are going to propagate and remove the value 1 for all the other all the other letters, okay? And that's essentially the state of the search space after this, you know, couple, you know, this not equal and this equality constraint, the last equality constraint that you saw there, okay? So not very interesting, you know, right now. This is mostly what we have seen before. So things are going to get more interesting when you see this actual equation over there, right? And so now we have to find a way to actually process that equation, okay? So I'm here, right? And this is the equation on top of me, okay? So one of the things that we're first going to do is to take this equation and simplify it given the current state of the search space, right? So we know that m is the value 1, so when we see, you know, the value of m, we can replace that by the value of 1. So the equation becomes a little bit simpler, okay? And now what we're going to compute is, we're going to make sure that this constraint can be satisfied, we're going to compute the value, the set of values at the left of the equations and the set of values at the right of the equation, okay? And obviously, these, you know, there has to be a non-empty intersection between these two things, okay? So we're going to compute the range of the left and the range of the right of the equation, okay? So the range of the left is 3, 11, okay? And I want to go slowly and tell you how we get that, because this is kind of interesting, okay? So we have to, so this is essentially how you compute it, okay? And every one of these values that you see there is computed in a very systematic fashion, okay? So look, the 0 which comes here, okay, the 0 which comes there, comes from the value of the carry 3. Okay, so we have two possible values for carry 3, 0 and 1. Okay, now if we try to bound, you know, to have the smallest possible value for this left turn, we take the smallest value for carry 3, and that's 0. And that's the 0 that you see there. Okay, so the value 2 there is the same thing for s. Okay, so we look at what is the smallest value that s can take, and that's what you see over there. And then obviously we get the 1, which is the value of m that, you know, that is already fixed. Okay, and so this is the lower bound on the value of this expression in the current search space. Now we do the same thing for the upper bound, and in the upper bound what we are trying to do is to find a maximum value for that term. Okay, so when we see a variable like carry 3, we take the largest value. In this particular case, it's 1. Okay, then we do the same thing for the value of s, which is 9. Okay, and that's the value that you see there. Okay? So that's the value of 9. And then we also have the 1, which comes from the value of m, okay? And that's how you get 3 to 11, okay? And we can do that, and we can do that for the other side, which is basically giving us 10 to 19. I won't go into the detail. I won't bore you into the detail. But at this point, essentially, I know what is the range of the left side. I know what is the range of the right side. Now, to have a solution to these constraints, the intersection between this the range of the left and the range of the right sides have to be non-empty. And so this is what I'm computing here. I'm basically looking at these two ranges and taking the intersection, and the intersection has to be, you know, 10 to 11. Okay, so now I know that this intersection is not empty, so at this point, you know, I believe that there is a solution. Okay, so I also know more information. I know that this term here has to range between 10 and 11 if I have a solution, and same thing, of course, for the other term. So I'm going to use that information to start pruning the search space, okay? So what I know is that if I take the left term, okay, I know that it has to range between 10 and 11, okay? And now I'm trying to say, oh, but how can I prune the search space using that, okay? So let's, you know, remove all the mess, and now I have just this equation there, okay? And I see that, you know, 10 has to be smaller or equal to the carry 3 plus the value of s plus 1, and that has to be smaller or equal to 11, okay? Now, let's assume that I'm trying to prune this, you know, to prune the value of s. What can I do? Well, I can first, you know, take the 1 which is in the equation and move it on the right and the left hand side. And then I have to say, oh, I have to remove this carry 3, right? So I'm going to push carry 3 on the left and a carry 3 on the right as well. And so now the value of s can be bounded by these two expressions that you see there, right? And so what I have to do now is, once again, I want to be very conservative here, right? So I want to see what is the smallest value that S can take, okay? And I also want to see, but what is the largest value that S can take? So when I evaluate this expression, I have to find a way to find the smallest possible value, because if I'm not conservative, I can prune solutions. And the only thing that I want to do is prune values which appear in no solution. Okay, so what I'm going to do here is to look and say, okay, the left-hand side, okay, has to be made as small as possible. How do I do that? Well, I have a minus, carry 3, so I have to make this carry 3 as large as possible, because if it's large, then I subtract a lot of values, and that value becomes very small. Okay, so how do I make carry 3 as large as possible? I take the value 1 for that, okay, and I take the value 0 to make it as small as possible, such that I have the largest term on the right of the equations. Okay, so essentially what I get there is that the value of S has to be essentially greater or equal to 8 and smaller or equal to 10. Okay, so this is interesting, right? So because at this point I can prune the search space dramatically for S, right? So I remove all these values up to 8 and 9. Okay, and this is what this equation has told you, and I have only looked at one side of this equation essentially, right? So if I look at the other side, okay, I know I have to make sure that this side now also range between 10 and 11. Okay. And so I can do exactly the same reasoning. Okay, so I take these two things, I put them there, and assume that I'm interested here in looking. I know already that the carry 4 is equal to 1, so I get this expression here. Okay, and then I can prune the value of O at this point. Okay, and it basically becomes O has to be basically between 0 and 1, and I can in one step prune a lot of value for O as well. Okay, so all these values here, for letter O has been removed. At that point there is only one left, which is 0, so I'm going to assign it. As soon as I assign it, all the not equal constraints linked to that variables are going to start, because now that variable is only one value. That's when these constraints are propagating. Remember last lecture, okay? And so in a sense, all the other variables there are going to propagate there using these not equal constraints, okay? So that's what you see there, okay? So we go back to these constraints there, propagate them, and now the search space has been reduced, and the only variable, the only letters that can take the value 0 is O, okay? So what we have done so far is propagating all the constraints up to the one which is highlighted there. Okay, so we propagated the non-equality, the very simple equality, the first equation, and we are looking at the second one now. Okay, second one is exactly the same reasoning as I've shown you. We are looking at these equations like that, and we're going to do the bound reasoning that I've shown you, right? We simplify it a little bit using the value of the variable. We know that this guy is between 2 and 10. Okay, if this guy is between 2 and 10, we know that this guy, to satisfy the constraints, has to be between 2 and 10, and that's what we are looking at. Okay, so now we know the value of n. Okay, plus 10 times the carry 3 has to be between 2 and 10. Okay, so let's assume that we are interested in carry 3. If we are interested in carry 3, we have to take this value of n and move it on the left and the right. Okay, so that's what we do. Okay, and this is what we get. We get 10 times carry 3 there. Okay, and then you have the value on the left and the value on the right for the lower and upper bound. Okay, now you look at this 10 times carry 3. So once again, we have to make this guy as small as possible and this guy as large as possible to be conservative, right? Okay, so to make this guy as small as possible, what do? We take the largest value for n. What is the largest value for n? It's 9. Okay, so and the other side, the upper bound, we have to make it as large as possible, and so since this value is negated, we have to make it as small as possible, so we take the value 2. Okay, so at this point we simplify the equation, okay, which becomes minus 7 is smaller or equal to 10 times carry 3, smaller or equal to 8. The left side is boring. Okay, so the right side is more interesting because it forces carry 3 to be equal to what? To be equal to 0. Okay, so this guy is not going to be 1, it's going to be 0. And now something really interesting happens, right? So what we just did now is looking at these second equations, and we found a new value here for carry 3. Now, the interesting point here is that carry 3 is also happening in the first equation. So now we are basically saying, ooh, but that equation has some more information. So I will go back and propagate that information, okay? So remember, the fixed point algorithm is always looking at this loop and always taking, looking at the constraints, and until you cannot propagate anything, it's going to look at constraints and trying to actually propagate them again. Now, when a value of a variable, like I've shown you here, okay, has changed, it's a good indication that you should actually reconsider that constraint. So the constraint propagation algorithm is going to take that constraint and try to propagate it again and try to, obviously, to find if it's still feasible and so on. Okay, so we're going to go back to that constraint. So this is the constraint that you see there. Okay, and we're going to simplify it because we have a lot more information at this point, right? So you see the value of carry 4, we know the value of O, we know the value of M, and so this constraint becomes really simple at this point. It becomes essentially the value of S is equal to 9, okay? So once again, what we can do is prune the search space, okay, and remove the value 8 from the value of S, assign the value 9. Of course, you're going to propagate all the non-equal constraints and remove all these values, and this is how the search space has been removed, okay, has been pruned at this point. Okay, so essentially what I've shown you here is how these constraints are basically, influencing every other ones. Okay, so constraints is going to propagate. Okay, use its dedicated algorithm to remove value from the variables. Now, some of these variables appear in other constraints. These other constraints are going to be propagated again, remove more values, which are going to propagate other constraints, and so on. And this fixed point algorithm is really what is the core of constraint programming. So you basically propagate all these constraints until you cannot deduce anything. And also, you have a dedicated algorithm for every one of these constraints. Okay? So let me go into a little bit about the mathematical details to actually implement this, which are reasonably simple here. Okay, so this is essentially this is a linear inequality that I'm going to show you how to propagate optimally. Okay, so you see that the left hand side here is basically a sum of product. Okay, ai xi. Xi are decision variable. Ai's are basically constant. So that's the left hand side. The right hand side is similar. Okay, the y's are basically decision variables. The b's are constant. Okay, and so what I'm interested in here is essentially propagating that constraint optimally, removing as many values as I can from the domain of the variables. So I'm going to assume that the domain of xi and yi are denoted with the convention that I used last time. So dxi is the domain of xi, and dyi is the domain of yj. And now what I have to do is to propagate using that information these constraints. Okay, so the first thing that I have to do is to test if it's feasible. Okay, and the feasibility test here is going to be very, very simple, right? So how do I make sure that I can, how do I test, if this constraint is feasible given these domains for these variables? Well, what I want to do is essentially take the left-hand side and make it as large as possible, right? And take the right-hand side and making it as small as possible. And if the smallest value and the largest values don't satisfy the constraints, I know that nothing will satisfy the constraint, okay? So the feasibility test, look at the left-hand side and replace every decision variable by the maximum value that it can take. It look at the right-hand side and look at every decision variables and take the smallest value that it can take, so that's the min in this domain. And then I test, no, I have no decision variable left, only constant, and then basically test if this inequality is satisfied or not. Okay, if it's satisfied, it's feasible. If it's not, it's infeasible, right? So now essentially, let's assume that it's satisfiable. Okay, otherwise I can't prune, right? I have already pruned the node in a sense, and so what I'm going to assume here for pruning is that I have two values left, L and R, for left and right, okay, which are basically, the L is basically denoting the largest value that the left-hand side can take, and R is denoting the smallest value that R can take, okay? So I'm going to use that for the pruning algorithm. Remember, L is the largest value for the left-hand side, R is the smallest value for the right-hand side, okay? So then this is how I prune the search space, okay? So I want to look at xi, okay? So let's look at xi. Okay, so what I know is that AIXI has to be greater than what? So look at this. Look at the initial constraints over there. I'm going to look at the right. I'm going to look at the right-hand side. Okay, so the right-hand side is R. Okay, so that's going to always be there. And then what I have to do is take all the other variables here, okay, and move it on the other side. So they have the largest value there, and those values are essentially L, except that I don't want to double count xi, right? So I have already counted inside I have already counted inside L, so I have to remove it. I have to remove AI times the domain of times the largest value in the domain of x of xi, and that's what I'm doing in this expression here, right? And so now I know that this is valid. Okay, so I know that AI xi has to be greater than that for the constraint to be satisfied, and that gives me this pruning rule that you have here. Okay, so I basically take this expression, divide it by AI, and since I want to be conservative, I have to round. Well, that's fine. So since I'm working with integers, I have to round up, of course, if it's a fractional values. Okay, and this is what you see here. Okay, so this is what you see here. Sorry. So what you see there is that I'm basically taking the seal of that expression over here, okay? And this is how I prune. And of course, for y I'm going to do exactly the same thing, except that I'm going to subtract the value of yj, and then I'm going to divide by bj, and then instead of taking the seal, I'm going to take the floor, and I'm going to basically update the upper bound of yj. So in a sense, so what I do is that I update the lower bound of the x's, I update the higher bound, the upper bound of the y's using these two very simple rules that can be computed efficiently, which essentially, as I told you, use the largest value for the xi in the domain of the xi and the smallest value in the domain of the yi. Okay, so lessons from this lecture. First, that you have dedicated algorithm for every one of the constraints. The constraint propagation algorithm is really rich. It's going to propagate these constraints until you cannot get information. And so as soon as you accumulate information on one variable, it's going to propagate to another one. You can come back and propagate all these constraints. Okay, and in this particular case, the bound propagation algorithm is very easy to compute. It basically reasons about the upper bounds and the lower bounds on every one of the variables. Okay, so we're going to see in the next couple of lectures, different modeling techniques for constraint programming and also different techniques for actually pruning the search space. Okay, see you next time.